If they did that mistake, they would get 26%. It's the wrong answer, but it's also listed as choice B. Mistake number 2. The student took the mass of barium, which is 0.47 grams, and simply converted that number into a percentage. They got 47%, which is the wrong answer, but that's listed as choice C. And mistake number 3, the student took the mass of barium, which is 0.47 grams, and divided by 0.80 grams, which is actually the mass of the precipitate and not the mass of the mixture. Welcome to AP Chemistry Review and Practice. My name is Michael Faribaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 1.4 to 1.6. As you can see on this slide, these topics fall under Unit 1 in the AP Chemistry curriculum, Atomic Structure and Properties. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 1.4, Composition of Mixtures. Here are some essential knowledge statements from the AP Chemistry course and exam description. Pure substances contain atoms, molecules, or formula units of a single type. Mixtures contain atoms, molecules, or formula units of 2 or more types whose relative proportion can vary. Elemental analysis can be used to determine the relative numbers of atoms in a substance and to determine its purity. Now let's move on to the practice for topic 1.4. This is question 1. Answer the following questions related to sodium sulfate, which has the chemical formula Na2SO4. In part A, we need to calculate the percent of sodium by mass in a pure sample of sodium sulfate. So that would actually be topic 1.3, elemental composition of pure substances, but we will see in question 1, part B, they're going to be talking about a mixture or a substance that contains an impurity. But here we are in part A. Calculate the percent of sodium by mass in a pure sample. Now this will start with a calculation of the formula mass or the molar mass of Na2SO4. So if you look on the periodic table, you will see that sodium has a mass of 22.99, sulfur has a mass of 32.06, and oxygen has a mass of 16. So in this chemical formula, we have 2 sodiums, 1 sulfur, and 4 oxygens. So the formula mass of Na2SO4 is 142.04, which is also equal to the molar mass, the number of grams in 1 mole. Now for the percent of sodium by mass, it's going to be the mass of sodium divided by the formula mass or the molar mass times 100. So I'm going to put 22.99, which is the mass of sodium, into this calculation. So take a look at my setup for this calculation. I've got 22.99 on the top, and then 142.04 on the bottom times 100. I'm just going to pause for a moment. I'm hoping that some of you watching this video will notice a mistake. Now, in fact, the correct setup for this calculation would be to multiply the mass of sodium by 2. So I did this on purpose. On the chemistry exam, the AP chemistry exam, this is an example of a common student mistake. Students would set up the calculation for percent sodium by mass by using the mass of only one sodium, 22.99, instead of using the total mass of sodium that is present in 1 mole of Na2SO4, and that would be 45.98. So here is the correct setup for the calculation. Total mass of sodium, so 45.98, divided by the formula mass, or the molar mass, and when we do that math, we get 32.37% sodium by mass. Again, this was for a pure sample of sodium sulfate. So now in part B, we're going to see it involves a mixture or a sample that contains an impurity. So here is part B. In part B, it says, a chemist analyzes a sample of sodium sulfate that contains an impurity and determines that the sample contains 29.5% sodium by mass. Again, you can see that the answer to part A, 32.4% sodium by mass, would be for a pure sample. So the 29.5% sodium by mass, that's for the sample that contains an impurity. Now in part I of part B, it says, which of the following substances is most likely to represent the identity of the impurity present in the sample that was analyzed by the chemist? Answer by drawing a circle around one of the choices shown below. So we have 3 substances: sodium chloride, NaCl, sodium bromide, NaBr, and sodium carbonate, which has the formula Na2CO3. Now, before we analyze these 3 substances, suppose for a moment that this impurity present in this sample were a substance that does not contain any sodium. So examples of this type of substance would include water, H2O, potassium chloride, KCl, glucose, C6H12O6. So if we had an impurity that did not contain any sodium, then any impurity that does not contain any sodium would cause the percent of sodium by mass in the mixture to be less than 32.4% sodium. So at first glance, you might feel that this question's a little challenging since each of these substances listed in part BI contains sodium. So since each of the substances listed in part BI contains sodium, what we need to do is to calculate the percent of sodium by mass in each of these 3 substances. And we are looking for a substance with a value for percent sodium by mass that is less than 32.4% sodium. That would cause the mixture to have a percent sodium by mass that is less than what we find in pure Na2SO4. So I'm going to start with NaCl. We're going to calculate the percent sodium by mass in each of these 3 substances. So sodium is 22.99 on the periodic table. Chlorine is 35.45. The total formula mass would be 58.44. Mass of sodium divided by formula mass would be 22.99 divided by 58.44 and then times 100. So take a look at our answer, 39.3% sodium by mass in sodium chloride. But we are looking for a substance with a value for percent sodium by mass that is less than 32.4% sodium. That was our answer to part A. So we can eliminate sodium chloride as a possibility. Now let's take a look at sodium bromide. Again, sodium 22.99. Bromine on the periodic table is 79.90. Formula mass 102.89. Mass of sodium 22.99 divided by the formula mass 102.89 and times 100. Now we get a value of 22.3% sodium by mass for sodium bromide. Again, we are looking for a substance with a value for percent sodium by mass that is less than 32.4% sodium. So it looks like sodium bromide is the correct answer to part BI. But just to make sure, to be thorough, let's go ahead and calculate the percent sodium by mass for sodium carbonate, Na2CO3. So we have 22.99 for sodium times 2, 12.01 for carbon, and then 16 for oxygen times 3. We get 105.99 for the formula mass of sodium carbonate. Total mass, again, notice I multiplied the 22.99 times 2. So total mass of sodium divided by formula mass times 100, and 43.4% sodium by mass, that number is larger than 32.4%. Again, we're looking for a substance with a value for percent sodium by mass that is less than 32.4% sodium, so we can eliminate Na2CO3. Now, in part B, double I, they would like us to justify our answer. So justify the choice you made in part BI by calculating the percent of sodium by mass for the substance that you circled and comparing this value to your answer to part A. So what I say here in part B double I is that the percent sodium by mass in sodium bromide is 22.3% sodium, and that is less than the percent sodium by mass in pure Na2SO4, which we had calculated in part A. So therefore, this impurity, sodium bromide, would cause the mixture to have a value for percent sodium by mass that is less than 32.4%. Now let's take a look at our next practice problem. This is question 2. Question 2 is a multiple choice question, and it begins with a student performs an experiment to determine the percentage of barium, Ba, by mass in a mixture of solid barium nitrate and solid sodium nitrate. So here is a beaker with a mixture of solid barium nitrate and solid sodium nitrate. The next step in the experiment is that a sample of the mixture is dissolved completely in water, forming a solution that contains the aqueous ions, barium 2+, sodium+, and nitrate NO3-. The next step in the experiment is that an excess amount of aqueous sodium sulfate is then added to the solution, resulting in the formation of a white precipitate, barium sulfate. So as you can see, there's a white precipitate of solid barium sulfate that is formed in this experiment. Now, the student collects the solid precipitate by filtration, dries the solid, and records its mass. Data from the experiment is shown below. So the question is asking, based on the information in the data table, the percent of barium by mass in the solid mixture is closest to, and then we can see 4 numerical choices. So the mass of the solid barium sulfate precipitate is 0.80 grams. Now, how much of that solid barium sulfate precipitate is actually just barium? So that's what we're trying to calculate initially in this problem. How much of that 0.80 grams of barium sulfate is actually grams of just barium alone? So we'd love to take 0.80 grams of BaSO4 and then calculate how many grams of just barium are present. So how do we get those numbers in that conversion factor to go from grams of BaSO4 to grams of just Ba? Well, we can use the information on the periodic table. So on the periodic table, we can see that barium has a mass of 137.33. And if you add up the mass of 1 barium, 1 sulfur, and 4 oxygens, you get a formula mass for BaSO4, which is 233.39. So if we pick up our calculator, we start with the mass of the precipitate, which is 0.80 grams of BaSO4, and then multiply by 137.33, divide by 233.39, and this will tell us how many grams of barium are present in this precipitate. And so that works out to be 0.47 grams of barium. Now, the question is asking us to calculate the percentage of barium by mass in the solid mixture. So mass of barium divided by mass of mixture times 100. That's the calculation that we have to do to answer question 2. So we just calculated the mass of barium, which is 0.47 grams. Let's divide that value by the mass of the mixture, which is 3.10 grams. So 0.47 divided by 3.10 times 100, this gives us 15% barium by mass. So the correct answer to question 2 is choice A. Now, as an AP chemistry student, it's important for you to understand that the people who write multiple choice questions for the AP chemistry exam are well aware of common student mistakes. Here is our first mistake. A student took the mass of the precipitate, which was 0.80 grams, and they divided by the mass of the mixture, which is 3.10 grams. If they did that mistake, they would get 26%. It's the wrong answer, but it's also listed as choice B. Mistake number 2. The student took the mass of barium, which is 0.47 grams, and simply converted that number into a percentage. They got 47%, which is the wrong answer, but that's listed as choice C. And mistake number 3, the student took the mass of barium, which is 0.47 grams, and divided by 0.80 grams, which is actually the mass of the precipitate and not the mass of the mixture. They got 59%, which is the wrong answer, and that is listed as choice D. So again, the people who write the questions for the AP chemistry exam are well aware of common student mistakes. So correct answer to question 2 is 15% barium by mass. That's 0.47 grams of barium divided by the 3.10 grams, the mass of the mixture. Now, let's move on to the review for topic 1.5, atomic structure and electron configuration. Here are some essential knowledge statements from the AP Chemistry course and exam description. The atom is composed of negatively charged electrons and a positively charged nucleus that is made of protons and neutrons. Coulomb's law, and this equation is featured on the AP Chemistry equations and constant sheet. Coulomb's law is used to calculate the force between two charged particles. In atoms and ions, the electrons can be thought of as being in shells or energy levels and subshells or sublevels as described by the ground state electron configuration. Inner electrons are called core electrons, and outer electrons are called valence electrons. The electron configuration is explained by quantum mechanics as delineated in the Aufbau principle and exemplified in the periodic table of the elements. The relative energy required to remove an electron from different subshells of an atom or ion, or from the same subshell in different atoms or ions, the ionization energy, can be estimated through a qualitative application of Coulomb's law. This energy is related to the distance from the nucleus and the effective shield charge of the nucleus. Now let's move on to the practice for topic 1.5. This is question 3. Titanium, which has the symbol Ti, has several common oxidation states. Answer the following questions related to titanium. Part A. Write the complete ground state electron configuration for a titanium atom. Now, as you can see on the periodic table, titanium has atomic number 22. So we have to start with the electron configuration beginning with energy level 1. That would be 1s2. And then moving on to energy level 2, that would be 2s2, followed by 2p6. This would get us as far as neon, atomic number 10, on the periodic table. Moving on, the next subshell would be 3s, so 3s2, followed by 3p6, This would get us as far as argon, or Ar, on the periodic table. Now we're in the fourth period. This would be 4s2. And then 3d. We're not going all the way to 3d10, which would be zinc. We're just going to titanium, so it's going to be 3d2. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. This is the correct answer to part A of question 3. Now you may know that there is a way of abbreviating an electron configuration using a noble gas. So if I put the symbol for the element argon, Ar, in brackets, this would be the noble gas abbreviated version of the electron configuration for titanium. So Ar in brackets, followed by 4s2, 3d2. But looking at the instructions for question 3, part A, they wanted the complete ground state electron configuration for a titanium atom. So I'm going to start with 1s2 and then write the complete electron configuration as follows. Now, moving on to part B of question 3. It says, when titanium forms cations, electrons are lost from which subshell first? Identify both the number and letter associated with the subshell. Well, the two choices that most students would make for losing electrons from titanium would be, are we removing electrons from the 3d subshell, or are we removing electrons from the 4s subshell? So in my video for topic 1.5, I had mentioned what we do when removing electrons from transition metals. Here's an example with a different element. This is iron. So iron has 26 electrons, and the last part of iron's electron configuration is 4s2, 3d6. And so in that video, I talked about what happens when an atom of a transition metal, for example, elements 21 through 30 and elements 39 through 48, when they lose electrons to become a cation, the electrons are first removed from the valence s orbitals. And if additional electrons are lost, then they are removed from the valence d orbitals. So when iron loses 2 electrons to become an ion with a charge of +2, the electrons are removed from the 4s sublevel first. And then if you have to remove another electron to go from iron 2+ to iron 3+, then that electron would be removed from the 3d sublevel. Now, back to this question. So in part B, it says, which subshell would titanium lose electrons from? And the answer is the 4s subshell. Now, as we see in part C, we have 2 ions. We have titanium 2+ and we have titanium 4+. Write the ground state electron configuration for each of the following ions. So let's take away 2 electrons from the 4s subshell. So for titanium 2+, that becomes 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d2. Now for titanium 4+, 2 more electrons are now removed, but this time from the 3d subshell. So for titanium 4+, it's 1s2, 2s2, 2p6, 3s2, 3p6. All right, well, those are the answers to question 3. Now let's move on to question 4. Question 4, which is a multiple choice question, asks, which of the following choices correctly identifies the number of unpaired electrons in the ground state electron configuration for an atom of that element? So we have nitrogen, N, selenium, Se, gallium, Ga, and silicon, Si. And the number of unpaired electrons is 1, 2, 3, or 4. So what we need to do is not only identify the correct electron configuration, we also have to know how to follow the rules for placing the electrons in those electron energy level diagrams that you may have seen before. Let's start with nitrogen. So nitrogen has atomic number 7, and its electron configuration would begin with 1s2, followed by 2s2, and then finally 2p, but we're stopping at 2p3. So here is the electron energy level diagram there would be 2 electrons in the 1s, 2 electrons in the 2s, and then 3 electrons in the 2p sublevel. We represent electrons as arrows, and if we follow the rules, this is what the electron energy level diagram would look like. So as you can see, there are 3 unpaired electrons for nitrogen. Now, going back to question 4, we can realize that it said 1 unpaired electron. That's why we can eliminate choice A. Let's move on to selenium, or Se, which is atomic number 34. So 1s2, 2s2, 2p6, 3s2, 3p6. Now we're in the 4th period. That would be 4s2, followed by 3d10. And then the last part of selenium's electron configuration would be 4p, but we're stopping at 4p4. I'm not going to show you the entire electron energy level diagram, but just the last portion, sublevels 4s, 3d, and 4p. Now the 4s is full, the 3d is full, so there's no unpaired electrons. But if we follow the rule for placing those last 4 electrons into the 4p sublevel, we see that there are 2 unpaired electrons. Considering that that is the correct answer to question 4, 2 unpaired electrons, that makes B the correct answer. At this point, I'll just confirm that choices C and D for gallium and silicon are incorrect. Now, gallium has 31 electrons. It's going to be completely full up through 3p6, followed by 4s2, 3d10, and hopefully you can see that there's only 1 unpaired electron for gallium. So the 4p1, that is the single unpaired electron. So that's why choice C is incorrect. And then finally for silicon, which is atomic number 14. So 1s2, 2s2, 2p6, 3s2, and then the final 2 electrons would go into the 3p sublevel. So you can see, just based on this portion of the electron energy level diagram for silicon, that would be 2 unpaired electrons for silicon. So that's why choice D is incorrect. So correct answer to question 4 is choice B, and hopefully you can see why selenium, with its 34 electrons and 4 electrons in the 4p sublevel, has exactly 2 unpaired electrons. Now let's take a look at question 5. Question 5 starts with the ground state electron configurations of atoms of 2 different elements are listed in the table above. And then it asks, which of the following statements correctly identifies the element with the higher value for its first ionization energy and provides the correct explanation based on Coulomb's law? Well, before we consider ionization energy, let's begin by identifying these 2 elements that are labeled as number 1 and number 2. We can see that they both have electron configurations that begin with 1s2, 2s2, 2p6, 3s2, and then 3p6. And then it's either 4s1 or 4s2. So we can see that this would be potassium and calcium on the periodic table. So element number 1 is potassium, and the electron configuration for potassium would end with 4s1. And then element number 2 is calcium. Its electron configuration would end with 4s2. Well, now that we know the identity of these 2 elements, let's consider how we can compare the value for the first ionization energy. So one of the essential knowledge statements for topic 1.5 says that the ionization energy can be estimated through a qualitative application of Coulomb's law. So with Coulomb's law, we're looking at the energy of the attraction between the nucleus and the electrons that are being removed. And it's related to the distance from the nucleus and the effective charge of the nucleus. Now, in my next episode for AP Chemistry Review and Practice, I will give you some practice problems for topic 1.7, which is periodic trends. And ionization energy is definitely one of the periodic trends that AP Chemistry students should be familiar with. Now, back to Coulomb's law, we're talking about the attraction between a positively charged nucleus and the negatively charged electron cloud. If we are comparing the atoms of two different elements that are located in the same period, such as potassium and calcium, then the valence electrons of each atom are located in the same energy level, such as the 4s sublevel for potassium and calcium. Now, the element with more protons, in this case calcium, should have a greater nuclear charge. There should be a stronger attraction between the nucleus and the valence electrons. So according to Coulomb's law, the greater the magnitude of the charge, the stronger the attractive force between oppositely charged particles. So it's calcium that has one more proton than potassium. The valence electrons of each atom are located in the same subshell, which happens to be 4s. Calcium has 20 protons, whereas potassium has only 19. In calcium, there is a stronger attraction between the nucleus and the valence electrons. So that's why it should require more energy to remove that electron from calcium as compared to potassium. So we're looking for, of the four choices, something that identifies element number 2, calcium, as the one with the higher value for the first ionization energy. So it's either choice C or D, based on choosing element number 2, but it's not about more shielding between the nucleus and the outermost electrons. It's about a greater attractive force because the nucleus has more protons. So the correct answer to question 5 is choice D. Element 2, because the nucleus has more protons, would have a higher value for its first ionization energy because there's a greater attractive force on the electrons in the 4s sublevel. Now, let's move on to the review for topic 1.6, photoelectron spectroscopy. Here is an essential knowledge statement from the AP Chemistry course and exam description. The energies of the electrons in a given shell can be measured experimentally with photoelectron spectroscopy, abbreviated as PES. The position of each peak in the PES spectrum is related to the energy required to remove an electron from the corresponding subshell, and the relative height of each peak is ideally proportional to the number of electrons in that subshell. Now let's move on to the practice for topic 1.6. This is question 6. In question 6, we are given a diagram, and it says, a partial photoelectron spectrum of pure carbon is shown above. On the spectrum, draw the missing peak that corresponds to the electrons in the 2p sublevel. Now, if you've never seen a photoelectron spectrum diagram before, there are some important details to pay attention to. Let's start with the y-axis. The y-axis is labeled as relative number of electrons. So that means that each peak in the photoelectron spectrum diagram represents the number of electrons in that particular subshell. Now for the x-axis, it's labeled as binding energy with units of megajoules per mole. Now the higher the binding energy is, it's actually located on the left. So if you look at the numbers on the x-axis, that is done in reverse order, but that is intentional. That is normally the way the x-axis appears, with the higher binding energies on the left and the lower binding energies down to 0 on the right. And the reason why that's done intentionally is that a chemistry student can actually read the electron configuration. So starting with 1s and then 2s and 2p and so forth, they can simply read the electron configuration from left to right across that diagram. Let's consider the details of carbon. So carbon has atomic number 6. That means that the electron configuration of carbon contains a total of 6 electrons. 2 electrons in the 1s, 2 electrons in the 2s subshell, and then finally 2 electrons in the 2p subshell. Now, the 2p peak is what we have to draw in this diagram, but let's consider the location of the peaks for 1s and 2s. Since the electrons in the 1s orbital are located closer to the nucleus, then they should be more difficult to remove. So the 1s electrons have the highest binding energy. So on this diagram, the peak that is located between 25 and 30 megajoules per mole, that would correspond to the 1s electrons. That means that the peak that would correspond to the 2s electrons would be located on the far right between 0 and 5 megajoules per mole. And now it is our job to figure out the location of the 2p peak on this photoelectron spectrum. And since the 2p electrons would be slightly easier to remove, a smaller binding energy. So the location of that 2p peak is right here on the diagram. So what I'm going to do is draw in red on this slide the location of the 2p sublevel electrons. So right here. And now just a final explanation about the characteristics of that particular peak. So we have 1s2, 2s2, 2p2. This is now the complete photoelectron spectrum of carbon. The peak that corresponds to the electrons in the 2p sublevel should be at the same height as the other 2 peaks because they each contain exactly 2 electrons. And then that peak should be located to the far right with a binding energy value that is less than that of the 2s peak, but obviously greater than 0. Okay, well, hopefully that answer and explanation makes sense. Now let's move on to another question involving photoelectron spectra. This is question 7. This is a multiple choice question, and it says the photoelectron spectra of the 1s electrons of 2 different atoms, fluorine and neon, are shown above. Let's be clear that we are not looking at a photoelectron spectrum of one pure sample of an element. Fluorine is 1s2, 2s2, 2p5, and then neon is 1s2, 2s2, 2p6. So in this diagram, we are just focusing on the peaks for the 1s electrons of fluorine and neon. And this question is asking which of the following correctly identifies the atom that is associated with peak X and provides a valid justification. So peak X is the one that has the higher binding energy. So the question we have to ask is, why do these 1s electrons have a stronger attraction to the nucleus? Now, in question 5 of this packet, we had been comparing potassium and calcium in terms of the ionization energy. So back in question 5, we decided that since calcium has one more proton than potassium, there was a stronger attraction between the nucleus and the valence electrons. That's going to be the same argument that we use to answer question 7. So we're talking about fluorine and neon. Neon has one more proton in its nucleus compared to fluorine, so there should be a stronger attraction between the 1s electrons and the nucleus of neon. So the correct answer is either C or D. We're talking about neon, but it's not because the nuclear mass is greater, it's because of the attraction for that positively charged nucleus. So it's because the nucleus of neon has one more proton than the nucleus of fluorine, so there is a stronger attraction between the 1s electrons and the nucleus of neon. So the correct answer is choice D, and it's based on a stronger attraction between the 1s electrons and that nucleus that has one more proton. Now it is time to move on to the next section of the packet. This is where I give you advice to help you avoid common mistakes. Now, my first piece of advice is something I had mentioned in the last episode of AP Chemistry Review and Practice, and that is read the question carefully and make sure you are answering the question that is being asked. My next piece of advice is to understand the difference between percent mass information for a pure substance, which is topic 1.3, and percent mass information for a mixture, which is topic 1.4. So see the bonus problem on the next page, and I'll go over that example in a little bit. Be familiar with the electron energy level patterns on the periodic table, such as 1s, 2s, 2p, and so forth, so that you can write the correct ground state electron configuration for any atom or ion. And then, as I had mentioned in this video for titanium as the example with 4s versus 3d, when an atom of a transition metal loses electrons to become a cation, the electrons are first removed from the valence s orbitals, and if additional electrons are lost, they are removed from the valence d orbitals. Now, this next piece of advice talks about learn how to apply your understanding of Coulomb's law when comparing two different particles. And I will have more to say about this topic when I get to our next episode of AP Chemistry Review and Practice. So that would be including topic 1.7, periodic trends. So specifically, here are some examples where you're comparing two different particles. Suppose that the valence electrons of each particle are located in the same energy level. Then the particle with more protons has a greater nuclear charge. The particle with more protons should experience the stronger attraction for the surrounding electrons. So in this example, we're looking at sodium and magnesium. The valence electrons of each atom are located in the same 3s subshell. The nucleus of magnesium has more protons than that of sodium. The attraction between the nucleus and the valence electrons is stronger in magnesium than it is in sodium. So we would expect magnesium to have a smaller atomic radius than sodium, and we would expect magnesium to have a greater value for its first ionization energy than sodium. Now, suppose that we're looking at two particles and there is a different number of occupied electron shells. The particle with the greater number of occupied electron shells should have a larger size or radius. The particle with the larger size should experience the weaker attraction for the surrounding electrons. So in this example, it's sodium versus potassium. So the outer electron for sodium is in a 3s orbital, but the outer electron for potassium is in a 4s orbital. So potassium has a greater number of occupied shells, so energy level 4, than sodium does, energy level 3. The attraction between the nucleus and the valence electrons is weaker in potassium than it is in sodium. We would expect potassium to have the larger atomic radius, and we would expect potassium to have a smaller value for its first ionization energy compared to sodium. Now, suppose that each particle contains the same number of protons, so it's the same element, and the valence electrons of each particle are located in the same energy level. If that's the case, the particle with more electrons should experience more electron-electron repulsions, and as a result of those electron-electron repulsions, it would have a larger size or radius. So in this example, we have iron 2+ and iron 3+. So because they are both iron, the nucleus of each ion has the same number of protons, which is 26. The valence electrons of each of these ions are located in the same 3d subshell, but Fe2+ actually has 24 electrons, and Fe3+ has 23 electrons. So since the Fe2+ ion has more electrons than the Fe3+ ion, that results in greater electron-electron repulsions within the 3D subshell. We would expect the iron 2+ ion to have a larger ionic radius than the iron 3+ ion. And then that comment about photoelectron spectra, learn how to interpret PES diagrams, so photoelectron spectra, in order to do the following. Identify the atomic orbital associated with each peak in the PES diagram, write the ground state electron configuration for the element and determine the identity of the element, and then be able to use principles of atomic structure to predict or explain the values for binding energy for different peaks in the PES diagram. And now it's time to go over that bonus problem. Again, we are comparing a pure substance with a mixture. So here is the pure substance. A chemist analyzes a pure sample of calcium chloride, which has the chemical formula CaCl2. What is the percent chlorine by mass in this sample? Let's start by calculating the formula mass, or the molar mass of calcium chloride. So that would be just like we did for sodium sulfate back in part A of question 1. Mass of calcium, 40.08, plus 2 times the mass of chlorine, 35.45. So there's the formula mass, 110.98, which is also the molar mass of calcium chloride. Now, the mass of chlorine divided by the formula mass, or the molar mass, times 100, that is the setup for the calculation that we're doing. Remember, it's the total mass of chlorine. So not 35.45, but rather 35.45 times 2, because there are 2 chlorines in the formula for calcium chloride. So 70.90 divided by 110.98 times 100, we get 63.9% chlorine by mass. Now, that was a pure substance. This next question is about a mixture. So what is the percent chlorine by mass in a mixture that contains 2 grams of calcium chloride and 6 grams of sodium chloride? So the percent chlorine by mass in the mixture will be the total mass of chlorine in the mixture divided by the entire mass of the mixture, which is going to be 8 grams in this case. So 2 plus 6 is 8. But here we have to process the fact that each of the components of this mixture contains chlorine in it. So we have to determine what mass of chlorine is present in 2 grams of calcium chloride. And we have to figure out what mass of chlorine is present in 6 grams of sodium chloride. Once we answer those 2 questions, we will add these 2 values together. And then we will take that total mass of chlorine in the mixture and divide by the total mass of the mixture, which again is 2 plus 6, or 8 grams of mixture. All right, let's start with what mass of chlorine is present in 2 grams of calcium chloride. Now, the missing numbers that I need to go from grams of CaCl2 to grams of just Cl are going to come from the periodic table. So chlorine weighs 35.45, but we have 2 of them in this formula, and the formula mass of calcium chloride is 110.98, as we saw earlier in the problem that I showed you. So 2 times 35.45 divided by 110.98. That's my conversion factor. So I start with 2 times this ratio, and I get 1.28 grams of chlorine. Now, I'm not done yet, but that is the mass of chlorine that is present in 2 grams of calcium chloride. Now I'm going to repeat that same process for the 6 grams of sodium chloride. So I have 6 grams of sodium chloride. Using the information on the periodic table, that would be 35.45 grams of chlorine for every 58.44 grams of sodium chloride. That 58.44 is the formula mass of sodium chloride. So 6 grams of sodium chloride times this conversion factor, and that gives me 3.64 grams of chlorine that is present in 6 grams of sodium chloride. So as I said earlier, we have to add these values together. So 1.28 plus 3.64 equals 4.92. Now we're almost done. The percent chlorine by mass in this mixture would be 4.92 grams of chlorine total, divided by the mass of the mixture, which is 8 grams, and then times 100. So when I do that math, I get 61.5% chlorine by mass. So now you've seen a good example of a pure substance, which is topic 1.3, and a mixture, which is topic 1.4. So now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 1.7 and 1.8. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.